Now, I'm certain there's some announcements out there that I'm missing. I think I saw some last weekend, but I wasn't at a printer, so I couldn't print them. And then yesterday and today, my office hours have been eaten up with a variety of things, registering students and dealing with stuff for the dean and answering questions for faculty and stuff. So I haven't found the things I wanted to print. Check your emails. Just about everything that I print off, it shows up in your email. So be sure you check your emails, keep up with things. Now, let's talk about how the class is going, okay? We are not quite midway through Chapter 6 yet, but hopefully today we'll pass the midpoint and get into the second half, which is magnetism, and get a decent start on that. Now, we're only going 2 hours a day of lecture, so we won't get as far as we did, say, last time, but let's go as much as we can. Then the next 2 hours will be the lab. Today's lab will cover the material for it in a very short while, and then we'll move on, like I said, into magnetism. And then the last 30 minutes is your test on Chapter 4. So hopefully you're ready for that. You've got your formula and equation sheets done, and you'll be ready for that. Yeah. On the slides, we're on 15 out of 41, so we're about a third of the way, a little over more than a third of the way through the slides for Chapter 6. All right. Doubt if we'll finish Chapter 6 today, but we'll get far enough along so that perhaps on Thursday in 2.5 hours, we'll probably get Chapter 6 completed. Which means then the last 2 hours on Thursday will be the third lab from Chapter 6. Sorry. It does pretty well for a while. And then it starts one of these fits, and it won't quit. Okay. Sorry about having to stop here. These are the hardest things to get to open. All right. So, Thursday, we'll either finish Chapter 6 or make really good progress, I think, on it, and then have time for the 2 hours lab at the end. That means then at Thanksgiving, y'all know about Thanksgiving, right? You have the whole week off. We don't, okay? Some people will be down in Montgomery at the statewide meetings. I'm not going. Most of us will be, probably, they never send out any word on this until the night before, something like this. But judging from past years, we'll have meetings over on the Birmingham West campus Monday and Tuesday. Usually most of the day, Monday and Tuesday. Then, on Wednesday, they usually set us free to come back to our offices. So I will be on this campus, as far as I know, Wednesday morning anyway. Okay. Now that leads to something else. Since the college will be open Monday, Tuesday, and Wednesday. Of course, it's closed Thursday and Friday next week. That's Thanksgiving. But it'll be open Monday, Tuesday, and Wednesday, at least Wednesday morning. Monday and Tuesday, full work days, 8 to 5 or whatever. However, on Wednesday, it's not a given, but they usually let people go home sometime in the afternoon. Seems like maybe one year they let people go around noon. Most of the time it's been like 1 or 2 o'clock or something like that. They don't have to let us go early, but Quite often they do. And sometimes different departments let them go at different times. So the whole purpose of saying this, if you have business with the college that you've been postponing or want to take care of next week, do it Monday or do it Tuesday. All the offices should be open, or Wednesday morning. Even though technically the college is open Wednesday afternoon, to find someone in the office that you need, I wouldn't bank on it on Wednesday afternoon. I don't know what time. There'll be somebody there probably a little bit into the afternoon, but since I can't tell you how long, that will be next week. Okay. Then we come back the following week. We have 1 week of class, and then we have class on Tuesday when everybody else, the full-term classes, are having final exams. Okay. So what we'll be doing then, like I said, we'll either get started in chapter 8 on Thursday if we finish chapter 6 then. But more likely, we might be wrapping up chapter 6 on the Tuesday after Thanksgiving. If we finish chapter 6 Thursday, next time we meet, then we'll have the test on chapter 6 the Tuesday when we come back. Okay? At some point, now if we don't finish chapter 6 then, we'll have the chapter 6 test on Thursday of the week after Thanksgiving. I'm going to try not to do that, but it might work out that way. Now, that Tuesday or Thursday of that week, we're going to have a long day of class because there's only one lab in chapter 8, and we won't do that till we get to the end. Chapter 8 is a fairly lengthy chapter, so the odds are, my guess is we'll have probably a long day on Tuesday that week, that after Thanksgiving. And if we had finished the chapter 6 on the previous Thursday before Thanksgiving, then we'll have our test on chapter 6 the last 30 minutes. Okay? That leaves us with chapter 8 to finish up on the Thursday after Thanksgiving. And I'm guessing we'll finish it in time to have the lab for chapter 8. If not, then the next Tuesday after that, we'll have the lab and the test on chapter 8. And that's going to be about all that we'll have for chapter, for that day. Then, on Thursday of that week, that's when your final exam is scheduled. Now, I'm trying to remember. It seems as if a couple of guys from the class came and asked me if they could take the final early because they had travel plans or something. You know, and I understand that. So I said to them that if we finish everything and there's time on Tuesday, after we take the chapter 8 test on Tuesday, then I would give people the option of taking the final exam on Tuesday or coming back the next Thursday. That's when it's scheduled. I'll be here both days, all day, from 3:15 until 7:45, both days. Y'all won't be, I'm sure, but I'll be here the full time. So that is something you can hold in reserve. If enough of you are planning to do that, we usually have pizza on final exam day, but quite often people do want to have it early. So we may have it that last Tuesday, and then anyone who wants to come back on Thursday to take the final can, but not everybody need to. So that's probably what we'll do. Now also, on that Tuesday, I'll be returning everything to you, which means if you have not turned in a lab or completed all your tests by that Tuesday, now it's not the Tuesday after Thanksgiving, the one during finals week, everybody else's finals week. If you haven't gotten things in by then, those are going to be zeros, okay? And those are not good. So please try to get everything caught up, if possible, before then, so I can get them all back to you on that day. If you are going to take the final on Thursday, you'll have everything in your hand to study. Okay, any questions on that? Okay, so that's how we're going to roll with it, I think. So let's go from current slide here. I thought if I talk long enough, some more people may come in, but that hasn't seemed to work. Okay, now I need you to remind me. My memory and my mark were that we did this slide last time. Did we? Y'all remember? When we talked about conventional current going one way from positive to negative, that's conventional current, electron current going the other way. We also had this in lab. I told you in class, remember this, you'll need it in lab. Okay? But it really doesn't matter. What matters is the field, the electric field, and that's what provides everything. Okay? So, did we get this one covered last time? My memory was we did. So, I think we're starting on this one this time. Is that right? Okay. There's not, it's on page 150, you'll see this. There's Diamond. Okay. Be sure if you want to get a recap on how the terms go in the end, listen to the first part of this on the YouTube video. Just went over that in pretty gory detail. Okay. The verbiage starts on page 149. The figure is on page 150. What are the actual mechanisms of current? Well, in liquids and gases, you have generally positive and negative charges moving in opposite directions. For instance, in the battery, okay? Let's picture your lead storage battery in your car, okay? If you picture that, you have the positive pole here, the negative pole here. Well, the positive charges, those are generally hydrogen ions, and things such as that are moving to the positive pole, and the sulfate ions are moving toward the negative poles. Now they have a series of plates there, so one's going one way, one's going another. That's why they say both positive and negative charges move in opposite directions. Now when they say gases, actually they probably should be saying plasma, because if you have a charged gas, that's no longer a gas, it's a plasma. That's exactly what's going on in these tubes. You have a very high potential difference created by the large capacitor that the large capacitor that's up here in these lights, quite often they're called ballasts. If you've ever been into a fluorescent light, you know there's a big box somewhere up there, pretty heavy. It's a huge capacitor built up a large potential difference, and that's what sends ionizes the gas and makes it a plasma, and the positive ions fly one way and the negative another. But of course, this is alternating current, so they're really doing this. I mean, they're changing direction faster than you can imagine, so they probably don't leave where they are very far at all. They just go back and forth, back and forth, back and forth, but that provides the energy to excite the phosphorescent material that's on the inside of the tube, jumping it up an energy level, and then when the charge passes, whichever way it's passing, then they drop back down and give off a photon of light. That's probably more than you wanted to hear. But in both liquids and gases, or plasma if you want to say that, you've got both positive and negative charges moving in opposite directions. In metals, however, which is what most of our wiring is, you have delocalized electrons free to move throughout the metal. Now, some people call this an electron gas. Since it's in a solid, that seems like a little bit of a misnomer. But as I think I pointed out to you before, you can find the periodic table somewhere in your chapter 8. I asked them to put it at the end of the book, but I think they just put it in chapter 8, which it belongs in chapter 8. But there is one in my book there too, but I asked them to put it here. I don't think they did. Your metals, where we have these, what I call free electrons, like free Willy, only it's electrons, okay? They occur mostly in the metals. And in the next chapter, we'll talk about how the metals here, these are in a different shell of your electron structure, and the outer shell where these are, those electrons sort of don't belong just to iron or to nickel or something else. It's just sort of free to move through. They don't belong just to one atom of iron or nickel or whatever, but they're free to move among all of them, among the matrix that makes up that metal. Okay? And like I said, sometimes they call that the electron gas. Now, here's the key, and this is the main reason. It doesn't matter what direction you're saying the charges are flowing. The flow of charge is not really the important issue. That is what we call current, the charge per unit area, but that's, per unit time. That's also perhaps just a construct, because what's really going on here is the electrons. This is if there was no field across this metal. Now, this is way too organized to represent reality. If they had really represented it well, it'd be just a mesh of positives and negatives all mixed up in here, randomly distributed. No field, nothing's moving. They vibrate and that kind of stuff, but that's all. But once you impose a field, now the electric field is in that direction. That's the direction a positive charge would move if positive charges were moving. But you see, in a metal, there aren't any positive charges moving. Those atoms are fixed in place. They're in the metal matrix or the crystal structure, whatever you want to call it. It's the electrons that are moving, okay? And this electron, it has no reason that I can think of that it wouldn't have gone toward that positive charge, but they showed it going toward that one. But then it sort of bounces off because the field's in this direction, the electrons move in the opposite direction. And by the time it gets there, it might bounce off of it and then head down this way. Perhaps because it's being deflected by that one because there's another negative charge, and they try to repel each other. And then why it wouldn't go here, I don't know. But they're just showing places it could go. It could even go up here, but the odds are it's going to trend this way. But this is incredibly slow, this drift velocity of the electrons, because they keep getting attracted by protons or nuclei and repelled by other electrons, so their route is very tortuous. It's not just you turn on the switch and there they fly, okay? They don't. They start bouncing, moving around, and move awfully slowly, okay? Because of all these interactions they have with everything else in the area. But it's not the electron motion that's important, it's the field, okay? The electron field is set up instantaneously. The electrons near it move, this one moves. They're all moving at the same time, generally in the same direction, if it's direct current. And it doesn't matter that they don't move very fast or very far, they're all moving. And they move according to the field, and since they're all moving, they're giving up energy to the source, the light, the speakers, whatever you're doing, your computer. That's what the load. They're giving up their energy to the load. So, even though the individual electrons don't move very rapidly, the field is set up instantaneously, and basically it goes at the speed of light and are very close to it. The field is set up, and they all start moving. The ones right over here, move at the same time the one right by the switch. As soon as the switch is closed, the current circuit is closed, then they all start moving. And that's why everything looks like it happens instantaneously. It's not quite. The electric field moves through, I don't know why they have through and at both in here, but moves at nearly the speed of light. Really light speed. So that's why you don't notice a delay. If you're waiting for this electron here to get there, it's going to take probably several minutes, okay? Not instantaneously. But you see this electron starts moving at the same time this one does, and they all do, and responding to that electric field. All right, does that sort of make sense? All right. Now, trying to find this equation here. Oh, there it is. Whoa. If you're following in your book, turn back a page or two to page 149, where we started, and here's the formula for current. And again, if you remember back from it was basically the second chapter we did when we first started talking about motion. We talked about a displacement or a distance. The time rate of change of distance or displacement is speed or velocity. All right, we got a new term there, and we can deal with that. But what about the time rate of change of velocity? Well, that's an acceleration. We can deal with that. That gives us something else to work with. Then, much later, we ran into the time rate of change of momentum. And actually, that was a force, okay? We usually call it mass times acceleration, but it's actually the time rate of change of momentum. And Ethan's here. All right, good deal. Now, time rate of change of energy is power. It's just all over the place. Well, if we define a term, well, let's take the time rate of change and see what we got for that. Well, we were talking about charges back at the beginning of the chapter. Well, let's take the time rate of change of charge, and that's current. How much charge is moving in a given time? That's current. Now, why they use the symbol I don't know any more than I don't know why they use Q for charge, okay? They just do. T for time, that makes sense, okay? But capital I, no reason for it to be capitalized, except that little I is used for lots of other things, so they use capital I. These are parameters, they're not units. If you did the units, what is charge measured in? SI unit for charge. Coulomb, time, second, and current would be ampere, exactly. Now, the Coulomb and amps are capitalized because they're named after someone. Charles Coulomb and Louis Ampere. Okay? Time measured in second, that's not named after anyone, so the second is also a little letter. Lowercase. So there's the units. The current is the charge per unit time, just like you see here. The unit for I don't know if I said that right. Between the costs. The current is charge per unit time. The units for current is ampere or amps. We use either one of them. Capital A because it's named after someone, Louis Ampere. In a direct current, the charges all generally move in one direction. Okay? That's what we did in the labs. They move in one direction. The lighting and stuff in here, that's AC, alternating current. But in direct current, the electronic devices are usually run by batteries, solar cells. What we were using were power supplies. Those usually produce DC direct current. Most of our electronic devices, that's what they use. And you might say, but when I plug in my phone, I'm plugging into the wall to do. Why are you saying that is a direct current? Well, I ask you to check next time, and I know that our phones the plugs that we have little, ours happen to be white boxes that plug into the wall. They're bigger than just a regular plug. Why? Because in that you're changing the AC current coming out of the wall into DC, direct current. That's what's charging your phone. Basically, if an object has a battery, it's DC. Your whole automobile, except for a couple little places, everything is DC. Because, guess what? Lead storage battery there. Now, how about that couple of places? What do you mean by what did I mean by that? Somewhere in your system, in your car, you've got a belt that is driving something other than the wheels or a fan or something like that. And that belt is driving your generator. The generator is a magneto and things like this. We'll talk about that a little bit later. And that's producing current. Now, normally generators produce AC, alternating current. But in your car, and we'll be doing this in the lab, not today's lab, but Thursday's lab, if we get finished far enough to do that. And that's going to be, in the old days, is what we're going to study, a split ring commutator. So halfway around, the current is going in one direction, and then when it was going to go over here, it was going to switch and be alternating current. What they do in a split ring commutator is right about the time it gets halfway, then it flips the polarity, and as it goes down here, then that's going, say if this is positive here and negative down here, it's going like this, and about the time it hits there, it flips and does positive and negative again, because you flip the polarity. So that creates a pulse direct current. Why do you have that in a car? So you can recharge the battery. If you were trying to recharge the battery with alternating current, it'd be charging, discharge, charging, discharge, charging, wouldn't do any good. But if with that thing. Now today they don't use that anymore. They usually use what they call a dual diode converter or something like that. If the automotive guys were here, they'd give the correct name for it. And that does the same thing as the split ring commutator did in the past. It changes the alternating current from the generator to direct current. Probably a pulse direct current, which is recharging the battery, if the battery needs that. Always is out there to do it if you do. And I guarantee you, when you first start your car, you're draining that battery. And for the next, I would say probably 30 to 40 minutes of driving, you're recharging the battery. And then after a while, it's pretty balanced. And you always are allowing it to charge, but it usually doesn't need to anymore. That's why if you have a weak battery, you want to get out there and run it for a long period of time between stops, because you're gradually going to run that battery down. All right. The alternating current, the charge motion is oscillatory. It goes just back and forth, back and forth, back and forth. The electrons really don't go very far at all. They just go back and forth, back and forth, back and forth. If you measure total distance, they go quite a ways, but they don't ever leave the spot from very far. There's no net current flow, but there's always current. The movement of those electrons is current. So if you say, well, which direction, it doesn't really matter. They're moving back and forth. So there is current flow in AC. So you do talk about so many amps AC as well. The devices we'll be using today will be ammeters, which are measuring DC ammeters. But you'll see on the gauge there is a place for AC ammeters, but we're not going to be using AC, so you won't see those in practice. But if you'll notice the device, you'll see. Trying to think how they do it. I can't remember how they list them, but one's direct current ammeters and one's alternating current ammeters. Okay, so that was sort of a flashback to page 149. Now, and the second half that I was just talking about is the bottom part of the left-hand column of 151. There is a nice little illustration here I thought we were going to do, but it doesn't look like we are going to do it. Here's the spot. This is the figure 615 at the top of page 151. It shows a car. Now, I can't draw cars well, so don't laugh out loud, okay? If this is your car, okay, something like that. I think I got it going the wrong direction. It doesn't matter. Okay. And your battery is up here in the car. This is your battery. Okay. And your brake light is back here. Okay. There's your brake light. Okay. Now, electrons move very slowly in direct current circuit with a drift velocity of about, this is called the drift velocity of approximately 0.01 centimeters per second. Now wait a minute. What is that? Okay. Let me see if I have a dime in my pocket. If I don't, a penny will do. Ah, there's a dime. A dime is approximately the thickness of a millimeter. Okay? It's about the thickness of a millimeter. And 0.1 centimeters is a millimeter. So 0.01 centimeters would be if you took this dime and sliced it into 10 equal slices. If you can imagine how thin that is. The thickness of that, one of those slices, would be how far it moved in a second. In other words, the drift velocity would take 10 seconds to move through the dime. 10 seconds to move through the dime. That's not going very fast. And speaking of going very fast, here's Logan and Frank.
Don't forget Jay.
Huh? Oh. Well, I was wishful thinking. Okay. I know Frank's in there anymore. All right. Now, if you want a not too quick of a synopsis of how the end of the term's going to go, listen to the first part of the YouTube video. I'll probably say it again Thursday, so come to class on time Thursday and you'll hear us there. But we're just talking about cars, whether you can believe that's one or not. Okay? The battery in the front, the brake light back here. Okay? We just said the actual drift velocity of electrons through any DC circuit is about a hundredth of a centimeter per second. I was just saying, this dime is 1/10 of a centimeter, which is 1 millimeter thick, approximately. So if you slice that into 10 equal slices, if you can even imagine that, then that would be how far an electron would go in a second. So it would take 10 seconds to go the thickness of the dime. 10 seconds. So how long would it take the charge from the battery to reach this taillight? Okay? They do it in your text on the top of page 151. It would be more than 5 hours. 5.6 hours would be how long it would take this charge from the battery, if you stepped on your brake, to make its way back. They say approximately a 2-meter wire from here to there is approximately 2 meters. Okay? They put 2.00 meters. Okay? Approximately. And how long would it take that to go? Well, do the math and you'll find out it's in the neighborhood of about 5 hours. So no, we don't wait for the electrons to go that far, but as soon as you hit the brake, the field is set up almost immediately, as in near the speed of light, and then the electrons that are right near the brake light move at the same time this moves. They all move very slowly, but they move, and that's why the brake light comes on just like that. You don't get hit because you're waiting 5 hours for the light to come on. No, that wouldn't make sense. All right, any questions on that? All right, if you just came in, we're approximately page 151. And actually, I want to go back and look at the figure 613 on page 150. These are some of those high voltage towers, and it says, what is the nature of electric current carried by these conducting lines? Those guaranteed not direct current, alternating current, AC. It's an electric field that moves at nearly the speed of light. The field causes a net motion of electrons that constitutes the flow of charge. These being alternating, all the electrons are doing is just going back and forth like that. But all the electrons are going back and forth like that. So throughout the entire circuit. So that's where the energy is. Okay? And we'll learn later this is high voltage, which means very low current. We'll find that out later. Then on the top of page 151 on the right-hand column, whereas the car was on the left-hand column, myths, mistakes, and misunderstandings. What is electricity? It is not electrons moving through a wire at nearly the speed of light. As we just said, it's the field that sets up at nearly the speed of light. The electrons move so incredibly slowly. It's unbelievable. Okay. So, let's move on. Now, on page 151, we're hitting the next subtopic in this section, and that's electrical resistance. Anytime there's motion, almost any time there's motion, there's resistance. If your car's going down the highway at a low rate of speed, I remember doing this when I was a kid. It just seemed so fun to me. Stick my hand out the window. See, we didn't have air conditioning, so in summertime, spring, fall, and summer, the windows were always down. I like to stick my hand out the window. My dad didn't like me to stick my hand out, but I liked it. Going along, I could feel the wind. Now, when we were going at a high rate of speed, it almost took my arm off, okay? And that was sort of fun too, but not quite so much fun, okay? Anytime you're moving, there is resistance, whatever is moving. Well, electrical motion of charge also meets resistance. If you remember back that first figure we looked at, these electrons are getting bounced all over the place as they're trying to make their way down the wire, okay? There's other electrons, there's protons, there's matter, there's all sorts of things in the way. Well, there's always going to be resistance, okay? And when you have resistance, they lose some of their energy. What is energy per unit charge? Anyone remember what that is? Energy per unit charge. Voltage, exactly. Potential difference is energy per unit charge. So if they've lost some energy, they dropped in voltage. Not much, but a little bit. Now, two sources I just mentioned, collisions with other electrons. You wouldn't think they would collide. They probably don't actually collide, but they just get close enough to each other, they repel each other. So then ones get pushed backwards or sideways or something like that. Okay, the other is collisions with other charges in the material. Well, if it's not other electrons, the other charges would be positive charges, as in getting sort of close to a positive ion and then getting drawn in and sucked in and it's hard to keep moving, or a negative ion getting pushed back again like they did with the electrons. Okay? So other charges in the material. A guy way back, a German, named Georg Ohm, started studying this resistance to motion in wiring, in electric circuits. He found that the voltage was directly proportional I'm sorry, I should say it this way. The current was directly proportional to the voltage. This says it the other way, the voltage is directly proportional to the current. But what was, this one says it, current directly proportional to the voltage. But this factor here, your proportionality constant, for a given material, okay, or 1 over that for this rendition of it, that is what he named the resistance. The resistance of the material to allow the current to flow, okay? So, if you have a potential difference here, that's energy per charge, is equal to charges per second, then this comes out a bizarre set of units, but they decided to name that the ohm, after Georg Ohm, who did the studies on it. Okay? Now, since it's named after someone, wouldn't it make sense to use a capital letter to represent an ohm? But give me some number of ohms. Just make up a number. 400 ohms. So let's say we had 400 ohms. What's wrong with that picture? Second? Yeah, it looks like another zero. Because most people don't slash their zeros. If I hadn't slashed mine, you wouldn't tell if that was 400 ohms or 4,000 watts. So no, capital O would not be a good name. But it is an ohm, so what in the world are we going to use as the symbol for that? Well, when all else has failed before, like when we got to micrometers, whereas we had millimeters with little m, megameters with capital M, when we got to micrometers, we were running out of m's. So where did we turn? The Greek alphabet. And there we used a lowercase letter m. Now this is for meters, and that gave us micrometers, okay? Or micro ohms, or micro anything, but that's the symbol little m. So they decided to go to the Greek alphabet and see if they could pull up a symbol for a capital symbol. And Greek alphabet has lowercase and capital too. Well, their letter that corresponds to our O is Omicron. Mu, nu, Omicron. Just like M-N-O, they had mu, nu, Omicron. Well, they got to Omicron, and guess what it was? An O, okay? Yuck, that won't work either. But the Greek alphabet, and this is where it differs a little bit from in fact quite a bit, but not that major from our alphabet. They have a few fewer letters, period, but their last letter is not Z. Anyone know what their last letter is? Omega. Okay, and it starts with O. And they don't use the symbol O. There's their capital omega. And that's why they use that for ohms. Capitalized because it's named after somebody, and it is a Greek letter that sounds sort of O-ish. Okay? Anyone know what the first letter of the Greek alphabet is? Okay? So therefore the meaning for alpha and omega, beginning and end. Okay, very good. All right. So, that's how we came to use a Greek symbol, sort of looks like a horseshoe for ohms. Okay. Now this has nothing to do with what we're covering now, and you're not responsible for it, but I did want to give you this little tidbit that just shows how weird physicists are and how weirdly they think. Okay? This is resistance. There is another unit, another quantity that they decided was a convenient thing to measure sometime, and that's the opposite of resistance is called conductance. Where this was resistance, this was conductance. This is how much resistance it has, this is how well it conducts. And they did all sorts of studies with this, and they came up with a parameter, goodness, why can't I think of the word for it? The constant, the proportionality constant for conductance. And they needed a name for it. And it wasn't just one person that came up with this. A lot of people were using it. No one really was in charge of inventing it. So they needed a name for it. What name could they use for conductance? Anyone have a clue? Okay, I'll tell you. It's a mode. That wasn't because Larry and Curly's friend came up with it. That was a different one, okay? Y'all don't even know what I'm talking about there, do you? But they came up with this. Where did they get that name? Nobody was named Mo. That's exactly. They spelled ohm backwards. M-H-O. Art physicist strange. Okay? Totally strange. Okay, now what symbol would they use for it? Like I said, we've already used M for meters and MM for millimeters and capital M for megameters or mega anything. Well, M's have been used up. So what symbol would they use for a mode? Say again? Oh, well, mu is already used. Okay? So, and it's not really named after someone, so you couldn't use a capital mu. Here's the symbol they use for it. Now I'm serious. They took the ohm and flipped it over because it's reciprocal of ohm, so they just flipped the symbol over. Aren't they weird? Okay? Totally weird. But you're not responsible for that part, except how weird they are. Okay. So here are two expressions of Ohm's law. I'll get all this mess out of the way so you won't be distracted by it. V is equal to IR. Now sometimes they'll say this is E is equal to IR for electromotive force. Our book doesn't use that, but you'll see that sometimes. The problem with it, E is sometimes capital E is used for energy, and that's not the same as voltage. The volts are energy per coulomb, it's still not the same. But E is equal to IR. Okay? This book uses V, so stay with V. I think I told you before, V is both the parameter, it's also the unit, capital V named after voltage. Okay, and then if you express it in terms of current, current is voltage divided by resistance. Give me the one other, same formula, saying the same thing but in different order. What would be the third rendition of Ohm's law? Here you solve for V, here you solve for I. R is equal to V over I, perfect. All three of those are legitimate expressions of Ohm's law. This is expressing voltage in terms of current and resistance. This is current in terms of voltage and resistance. This is resistance in terms of voltage and current. All right, good deal. All right, any questions on Ohm's law? That basically is today's lab, okay? We're going to be focusing on Ohm's law. And by the way, just in order to say it one more time, in terms of units, using this one, an ohm is a volt. We use the same symbol for volt as we do the parameter over current. So 1 ohm is equal to 1 volt over 1 amp. Okay? So these are the units, those are the parameters. Any questions? Okay. And by the way, Ohm, if you remember back, the earlier guys lived around the time of the French Revolution and the American Revolution. Ohm came along after the American Revolution, just about the same time we started with our Constitution, and lived until almost the time of the war between the states, okay, 1789 to 1854. So the discovery of resistance came along considerably after current and voltage. Okay, so let's move on. Now, more on resistance. There are several things that affect resistance. One of the major ones is what kind of material are you dealing with. If you're dealing with silver, you have the least resistance. you'll find in any common material. Of course, silver, unfortunately, is not that common. It's pretty expensive, okay? Copper is right behind silver, much cheaper, much more prolific. You have more of it, and it's also much more flexible and stuff. So copper is next. Then you go on down the list. Aluminum is, whereas silver and copper are really close, aluminum's down here. Considerably more resistance than these two. But a pretty sad thing happened. Well, many sad things happened in World War II. Does anyone know what they use for shell casings? Say again?
Brass.
Brass. And brass is an alloy of copper, and I think either zinc or tin. I don't remember which. I always get those close up. It's which?
I think it's 10.
Tin, okay. I was thinking the same thing. Bronze is one and brass is the other. But copper's in both of them. Now, why do they use brass in shell casings?
Flexible.
Second,
Flexible.
it is somewhat flexible, but the main thing is that brass is non-magnetic, okay? It will not carry a magnetic field, and it's a pretty lousy carrier of electricity as well. Okay? And if you're dealing with weapons that could explode, you probably don't want stray sparks and things like this setting them off. So that's why they use brass. But because in World War II, we were using a lot of brass. All those bombs, all those projectiles that we shot from our tanks, our ships, our cannons, and everything else had brass casings. Bullets, tons and tons of bullets, they had brass casings. So we were using our copper like crazy, okay? Because we were using the copper, it became pretty scarce and also controlled. The government was controlling the market on that, so they could have all the supply to make all the shell casings they needed. Well, few people were still building houses during the war, but they couldn't get copper for wiring. So they relaxed the codes and allowed them to use what's next down the list from copper, aluminum. But it's pretty far down the list. Okay? But for a while, during and maybe shortly after World War II, they had aluminum wiring in some houses, not all of them, in some houses. Do you think you can find any of these historic houses now?
No, I'm sure their wiring is no longer there.
You got that right. Those houses either burned down because there's more and more demand on electricity, started using more, they would heat up like crazy and burn. Or they were rewired, like you suggested that. One or the other, but you won't find any or many houses with that aluminum wiring. Because once the war was over, plenty of copper, all the copper went back into use as wiring rather than brass casings. Okay, so the type of material, that's a resistance factor. Okay? The length of your conductor is also a resistance factor. Okay? I don't know if you've ever had this experience, but there was an ice storm, a really severe ice storm. It hit Birmingham. Remember, I think they call it Snowcopolis or something like that, where everybody had to just leave the cars on the road because they couldn't drive. The roads were just sheets of ice. Remember, this was probably 10 years ago, 8, 9, 7.
I think it was in 2011.
11, okay, 8 years ago, okay? That hit over in Georgia, I think, the next day. And over on the farm in Georgia, we hadn't built our house then, but where we built our house, no, we had built the house then. But in front of the house, we built it behind 4 gigantic, really old pecan trees, okay? And that ice hit, those limbs the ice coated the limbs. Some of those limbs crashing. And as they crashed, they broke more limbs, and more. So we had piles all over the farm, but especially those 4 trees, all over in our yard were just broken limbs everywhere. So we went out, cut the big pieces, threw those into the edge of the woods. The smaller pieces that were hard to pick up and stuff just went in the piles. And then sometime later, we decided to burn them. But for safety purposes, we wanted to run water. But the house is pretty far back from the road, so we took our hoses and as many hoses as I could piece together to run to go down. I still couldn't get to that farthest pile of brush, which we were trying to burn first. And I noticed that when my wife would turn on the water up at the house, I'd wait and wait and wait, and when it finally came out, it would. Why? The greater the length of hose, the more resistance to the water flow, so there went all your pressure. Pressure is force per unit area. So the water pressure was next to nothing. It did dribble out, but it was awfully slow. Okay? So the length, same thing in a wire. In a wire. The larger the diameter, easier it is for the charges to move. Even though they don't move very fast, easier to move. This tinier wire, there's more resistance on the edge than there is in the middle. So the smaller the wire, more and more resistance. So the length of the wire made a difference. Oh, and that led to cross-sectional area. I'm sorry, I got them crossed up. Cross-sectional area, the smaller the wire, just like that hose. Okay? If I take my thumb and move it over the opening of the hose, now less water comes out. Comes out, spews out fast because I'm spraying it. But the less water comes out because there's more resistance with a small cross section than with a large cross section. And then the final thing, or another thing, is temperature. How would temperature affect current or resistance? More resistance, because the molecules are bouncing around with increased temperature, increased kinetic energy. That's exactly what temperature is. Increased kinetic energy, meaning increased velocity, so they're bouncing around harder. So that electron trying to make its way down gets hit harder, bounce back and stuff, harder for it to make its way. So here are the 4 major resistance factors when you're dealing with creating resistance. Okay. Now I want you to think about, and I think y'all are old enough that you know what an incandescent light bulb is, right? I know you see lots of fluorescents these days. You see lots of LEDs. I think that's what's in here. And remember the compact fluorescents. But before those, you had incandescent light bulbs. How did they work? Do you know? Say again?
They use the filament.
They use a filament. And what did that filament do when electric? It got so hot that it glowed. And it happened to be a filament made of a material that glowed fairly white light. Okay? So that's why they use the filament. So they needed a lot of resistance. So the number one thing that good old Thomas Edison did, and it took him hundreds of trials to come up with what the best material for the filament was. I don't know if that's what they still were using, but I think he started off with tungsten. Tungsten filament, much more resistance than copper. Copper wire, never going to get hot enough to glow, or if it did, you're using a lot of energy to get it hot to glow. Okay, tungsten though had enough resistance, it would glow a whitish color pretty quickly. But not just that. Have you ever noticed those filaments in those incandescent bulbs? Notice anything about them? Yeah, they're little coils. I mean, just tightly wound coils of coil. Just think if you stretch that thing out. It'd be much longer than that, So that's how they got the length, by making them in coils. And have you ever noticed anything else about that wire? it is so incredibly tiny. Okay, about maybe a little bit more. I've got a few hairs here. That okay, about the thickness of a hair. A little bit more maybe, but not much. Okay, so very small cross-sectional area. Now, this has nothing to do with creating light, but it has something to do with light bulbs. When in your life have you ever had a bulb blow out? What were you doing at the time the bulb went out? Most of the time. Second? When did it go? Right when you turned it on. Okay? And why was that? Okay? Well, if you think back to Ohm's law, same voltage was across that wire. But if the resistance was less, the current was more. And the greater the current, the more likely we are to blow it. And what was the temperature of that light when you first turned it on? Room temperature. It was cold. That's why very seldom does the light bulb blow out when it was burning. Now, it does happen. Of course it will happen. But it's much more common for it to happen right when you turn it on, because the wire is cold, so more current surges through it, and if the wire is weak, it blows. Okay? And it's always older bulbs that the wire has gotten weakened. So you see all four of those are involved in the nakedness of light bulb. This is what makes it blow. Now, that leads to another thing. I think some of the temperature measuring devices in cars are called thermistors. Okay? Where that comes from, it's temperature measured by the amount of resistance that device is measuring. This is your surrogate, the resistance for temperature. And this is usually pretty high temperatures, aren't they?
Pretty high.
Pretty high, okay. I just know they use them. I don't know where they use them. All right, now, an exception. And there's always these exceptions. There are things that they've discovered named superconductors. These have negligible resistance. Some people actually say zero or no resistance, but they only occur at very low temperatures. So that drop that temperature. Now here's the strange part. Our very best conductor, silver, at normal temperatures, doesn't make a very good superconductor, no matter how chilled you get it. Same thing with copper. Same thing with aluminum. Most of the things that they have really weird materials that when you drop them cold enough, suddenly the resistance almost disappears. Okay? Now, the reason this was very late in being discovered, as in maybe not during your lifetime, but perhaps during mine, I don't remember when the first one was discovered, maybe before I was born, but they didn't have the technology to get temperature low enough to hit the superconductor. When they finally were able to get temperatures low enough to, can't remember if it's condense helium or freeze helium, one or the other. That's finally when they discovered superconductivity. That's how cold they had to get it. And it was rather odd materials. And for the next generation or two, I guess generation and a half or something like that, more and more work has been done to try to find different materials that would superconduct at slightly higher temperatures, as in liquid nitrogen rather than liquid helium. You know, helium, it's really cold before you can get it to, or hydrogen, maybe liquid hydrogen. Very, very cold. But when they finally, and they have gotten a few, so this is probably an overstatement, and I don't have the foundation for it, but it seems like to me just about as many Nobel Prizes have been awarded to different researchers in superconductors than just about any other field I know, because every one is sort of a breakthrough. So, anyway, that's what superconductors are. Now, I've left off one thing. Well, let's see. They left off the formula. They actually don't give you the formula. It's my other physics class that the students had to do this one. You don't, so count yourself lucky. But example 6.3 deals with Ohm's law, not with resistivity. We haven't mentioned that. Okay, come on, where is there? All right. All right, here we go. Got to go back to my car. Too bad, got to erase my car. Good. On page 152, example 6.3, a light bulb in a 120 volt circuit. Now, what does that tell you about the circuit? If you see 120 volts, it's what? You better believe it. Have you ever seen a 120 volt battery?
Your DC batteries for your hybrid.
Really? How much are they?
300 volts.
Really? Those are monster batteries, aren't they?
When you do your training on, they got this like, it looks like a pool hook.
Yeah.
They call it the shepherd's hook. That's what they pull the bottom off of that battery. So if you ever get stuck to it, you spray it.
They actually pull the body off to get to the battery?
No, they pull the body off the thing like when
Oh, I
we
see.
go to our test center. If somebody's stupid enough to have like conductive metals on them, that's what the shepherd took's for to pull the person away from the battery so they have something to put in the casket because it'll kill you on the instant.
Wow. Okay. I've seen some hybrid cars. I didn't know I was looking at a 200 volt, you said? 300 volt battery. DC. And those are lithium mostly, aren't they?
Unless you're in a Prius is a nickel hydride, but the bolts and most of your normal ones are lithium.
Okay. Which are better? Do you know? Which are better?
The lithium hold more power, but they can get a little hotter.
They can get hot, is that what you said? Yeah. And they seem to be a little unstable too.
Right.
Yeah.
That's the problem that we.
Yeah.
And if somebody knows a lot more than me,
Right.
engineering on that.
Yeah. Well, the thing that I've heard about them, though they're getting better all the time, is that you'd have them, they'd be working, and then suddenly they just quit. And there's just not much way of telling, hey, this one's getting weak or something. But that's why I said unstable. But anyway, so 120 volts, most of the time you're dealing with AC. Now, I'm going to set up my circuit as if it's DC, but understand it's usually not. Okay? So I'll draw it like this. Though really, a AC, you would draw something that looked like a generator. We may see that later, but I'll do it this way. Okay? This is 120 volts. Our voltage is 120 volts. V is the parameter. V is also the unit. Okay? The 120 light bulb in this circuit is turned on. So here's the bulb. I'll do it like we did in lab. Okay? And when it's turned on, a current of 0.50 amps. Actually a pretty large current. Okay? Flows through the filament. What is the resistance of the bulb? How would you determine that?
We have to change the formula of VIR.
Yeah, and what would you change it to?
R equals
V over I. Perfect. And V is 120 volts. I is 0.50 amps. And what would be your resistance? 240 ohms. Okay, good. Excellent. Okay. Let's flip it around a different way. And this says what current. So this time and I didn't put I equal this. Okay. So this time we're going to we're looking for current. That's the thing we don't know. Flow through an electrical device in a circuit with a potential difference of 120 volts and a resistance of 30 ohms. So this may not be a light bulb, be something else, perhaps, but the resistance is 30 Is it 30.0 ohms? Just 30 ohms. Okay? What would be the current? What formula would you use?
You have to change the V equals IR.
And what would you change it to?
I equals V divided by R.
V divided by R. And V in this case is 120 volts. And your current and your resistance is 30 ohms. And you can wipe out the zeros and 3 will go into 12 for what? Amps. 4 amps. And that's your answer. Very good. Ohm's law, very neat tool. You probably used it a lot. Now, I don't know if this is helpful to you or not. I don't ever use it, and it sounds like Patrick probably doesn't either. But, oh, I hit the wrong key. Okay. When I was in the Navy, this is how they taught anything electric in Navy schools. They always used as many teaching aids as they could. You know, sailors. Never mind. We won't get into that. But anyway, they use something like this. I've seen it done 2 ways. A circle or a triangle. And it doesn't really matter. I sort of prefer the triangle, but circles sometimes are easier to do. Okay? When you have a 3-point equation like Ohm's law, 3 elements to it, and they're all related by multiplication or division. Okay? Now, it sounded like Patrick was always starting with V is equal to IR, right? If you're starting with that, put the thing that's by itself on top, V, and then put down here I and R, in whichever order you matter. It matters. Now, the horizontal line is a dividing line, and the vertical line is a multiplication line that's brought with a time sign. So if you're looking for current, I is equal to V over R. If you're looking for resistance, R is equal to V over I. If you're looking for voltage, it's I times R. So I don't know if you find that helpful, but it works for this and anything that goes together. Remember when we had speed, acceleration, time, you know, all those? Time is equal to distance, speed is equal to distance over time, okay? So the distance is here, the speed and the time goes there. It works perfectly. Acceleration is velocity over time. Velocity up here, acceleration time down here. I mean, everything that works like that type of a formula. We're going to have another one in just a few minutes. Another formula that works that same way. Anything you can set up this way, you can use these. I have to think of what the real answer is to get them to do, but they are handy. I've seen a lot of people go into a test. This was when I was in the Navy. First thing they write down on the page is either the circle or the triangle so they can remember how to do it. Okay, but that's up to you. All right. So let's get back to where we were. Now, electric power and electrical work. This is the next subtopic in your text on page 152. There are 3 circuit elements contribute to work. This was in your lab. Sorry we didn't get this far so you didn't know it. But you knew it. You got it. Your voltage source. That gives the charge the energy. Volts is energy per unit charge. So this is what gives energy to the system. The electrical device is what uses the energy from the system. That's your load. I think y'all like to call it. Okay? That's your what's using the energy. And then you have to have the conducting wires, because if you don't have a pathway for that to work, it's not going to work. Okay? So, what these things do together, it maintains that potential difference, your voltage source, across the device. Okay? That's why when I had the picture I had earlier, had the battery here, the light bulb here, the same potential difference here is the potential difference there. Here, it's a jump up, the increase in potential here, decreasing potential there because it's using the energy from the battery or power source. Now, the input wire is, okay, and again, this goes back to your conventional current versus electron current, but the input wire is at the higher potential, the plus, than the output wire. That's if you got conventional current. The output wire sometimes is called the ground in AC circuits. Here, a lot of automotive students always referring to ground, which is fine, okay? That's the negative side. No potential difference, there is no current. And that's why a bird can sit on a high voltage power line and not get fried, because there's no connection to ground, okay? Now, if you threw that bird a little wire and it caught in its beak, you have fried bird, okay? Because then it would be, of course, you may be fried too if you were still hanging onto the wire, okay? But the bird sitting on the wire, no problem, okay? So you have to have a pathway all the way around the circuit in order for potential difference to provide the energy that you're expecting. Now, we're moving to power in circuits. I want someone to remind me what power is. I've already mentioned it once today. I was giving examples of time rate of change. What is power?
Available. You can, I don't know how to word it. You can, it's what's available to run a circuit. So,
Okay, say again.
potential energy.
Okay, energy is involved. It's the time rate of change of energy. In other words, the time rate that you're using energy. Remember running the steps as opposed to walking the steps? The difference there was time. Same work done. You didn't do any more work running than you did walking. Did the same amount of work, same amount of energy. It's just the rate at which you were doing it. When you ran, you were doing it at a higher rate. So that's what power is energy per unit time. So power is equal to energy. Now this is E for energy per unit time. Now, what unit in of these here deals with energy? Voltage. Voltage is what? I've said that several times today in between coughs. Energy per unit charge. Remember, the voltage potential difference is how much energy you give each of those little charges. Okay? Now, is there anything that relates, we've used energy here, but we haven't used charge or time separately. Is there any quantity that relates charge and time? And we've mentioned that today. I'm pretty sure. Yes, we did. I remember. In fact, that's when I started the whole thing of time rate of change. What were we talking about then? Say again?
Is it work divided by time?
Not work. We've got work divided by time. That's power. What is current? The movement of charge. Current, I, is charge per unit time. Okay? Now, take a look at this. If we take energy per unit charge, voltage, multiply it by current, which is charge per unit time, the charges cancel out, and what do we have? Energy per unit time. So this is voltage times current. That's what power is. Electrical power is your voltage multiplied by your current. Does that make sense? Okay? If you keep up with your units, they are your friends. They will help you out big time. Okay? Like they just did. There it is. P is equal to IV. Okay? Power. Yes. Remember the units? What was unit for power? SI unit for power. In joule per second. Joule is energy. Joule per second, what is a joule per second?
A watt.
A watt? A watt, yeah, okay. It's a watt, okay? Y'all knew that. You measure power in watts and kilowatts, right? Okay? Now, current is used in, what units for that? Amps, and voltage is in volts. Okay, that was easy. Okay. So there is your power formula. And guess what? This is multiplication and division. This is just strictly multiplication. If you want to use your circles or your triangles, I'll just use triangle here because I sort of like triangles better. Okay? You put your P on top, your I down here, and your V down here. And now you can get two other equations out of this one. What would they be? Yeah, you just got that one. P divided by I equal V. There's one. I is equal to P divided by V. You got it. Okay? There are two more equations besides this one that are your power equations. Now, actually, you can come up with more. I know you want them, don't you? If you combine this with Ohm's law, someone tell me what Ohm's law is.
Voltage.
V is equal to?
Amperage times resistance.
I times R? Yep, amperage times resistance. Okay, so what if we put that right here? You'd have power is equal to current times resistance, because that's what voltage is, isn't it? That's I squared R. Okay? You talk about your power hogs, anything that uses a lot of current is going to make that your meter spin. Okay? Your heaters, your water heater, your stoves, your ovens, your electric strip heaters, anything like that, boy, are you using the power. Okay? So I squared R. Okay? Now, give me another form of Ohm's law. Solve for I.
I equals V divided by R.
V divided by R. Okay, let's go down to this one. Oh, this one will work too. Power is equal to V divided by R times V. Right? IV, I is V over R. So this is V squared over R. So again, anything that uses large amounts of voltage. Now, doesn't everything use the same voltage? No. What uses different voltage? Light bulb uses low voltage.
Stove.
What?
Stove.
Yeah, your stove is going to have one of those three-prong. That's a 240 circuit, as is your clothes dryer, and more than likely your hot water heater, if it's electric hot water heater, your AC units, if you have an individual unit. There are a few that run on 120, but most of the heavier duty ones are, same answer you gave before. What uses lots of current? Going to be probably using higher voltage too. Those are going to be your energy hogs. Bank on it. Okay. Now, I'm going to clear this stuff out of the way. There are how many power equations? 1, 2, 3 here, and 2 more there. Wow. The book didn't go through all those, but in case you ever need them. Now, that bill that you get once a month, what do you call that bill?
It's your power bill, but it's not really your power bill.
Why isn't it your power bill? What are you paying for? Okay? Electricity is sort of a nebulous thing, what you're paying for. You said electricity?
Yes.
Okay? Actually, what you're paying for is Energy. The energy you're using. The power is the rate of using energy. Energy is what you're paying for. And if you ever notice the units of what you're paying for, it's not kilowatts. Go home and look at your power bill and see what units you're paying. Anyone want to make a guess? It's kilowatt hours. You're absolutely right. A kilowatt measures power. Power times time. Guess what that is? Remember we said power was work per unit time. So if you multiply power by time, you get work or energy. That's what you're paying for. Kilowatt hours, which is an energy unit, not a power unit. So it should be your energy bill, is what you should be calling it. Why do we call it power bill? Well, because Alabama Power is the one that sends it to you. So we call it that. Now, actually, my grandmother, she always called it something else. She called it her light bill. Have you ever heard the older folks call that? Why? When they first ran wiring in her home, the first home that she ever had that had wiring in it, all they used it for pretty much was light. They had the stained wood stove or other stove that they cooked from, and everything else, heated from, and everything else. All they used that electricity for was for light. So she always called it the light bill. Okay. To her dying day, I think she called it the light bill, if she remembered anything her dying day. Okay, huh? Who does? They call it light bill. Probably the reason. Because generations have called it that, so you just keep calling it that. Okay. Okay. So let me get my scratch out of the way again. And the energy bill, electric bills, the cost is determined by watts, which is power, times time. Watts times time is energy, joules, times the rate. And the dollars per kilowatt. No, it's dollars. Okay. No, they got this wrong. That's dollars per kilowatt hour. That should have an H after it. Now let's see if they got it right in the book. They should. Yes, in the book they put dollars per kilowatt hour, not per kilowatt. You have to have that kilowatt hours in there. Now I really should have backed up before we got to that and done example 6.5 on page 154. Okay? A 1,100 watt hair dryer, 1.1 kilowatt heat. Anytime there's heat, you can count on that going up. Okay. So what is that? What do we measure in watts? What's that a measure of? Power, exactly. Okay? Is designed to operate on a 120 volt circuit. What's 120 volt measure of? Second? Voltage or potential difference. Actually, the best word is potential difference, but we call it voltage. Okay? How much current does it require? What formula would you use? Second? P is equal to IV. Okay, are you going to change the formula first, or you want to plug and chug or chug and plug? I don't care. Huh? Change it? And how would you change it? I is equal to? Second? P over V. You got it. So now we can just plug and chug here. That's 1,100 watts, which is joules per second. Okay, that's a watt. Divided by volts, 120 volts. Oh, this isn't going to work. Oh, let's just call it watts. Okay, watts, and this will be volts. Okay? And what do you get? Pull out your calculator. I'll just wipe out the zeros right there. That'll be fine. 110 divided by 12. Anybody? Second? 9.16. They probably are going to say 9.2 because this is only two significant digits, 9.2, what units? Amps. 9.2. Hey, that's a lot of current, folks. A lot of things you measured in milliamps or tenths of amps or things like this. This is 9.2 amps. That's a lot. All right, let's do 6.6. An electric fan, I'll do that under the bill here, is designed to draw 0.5 amps. What's that a measure of? What does that measure? 0.5 amps. That's current. And the symbol for it is I. You're absolutely right. Okay? In a 120 volt circuit, so 120 volts measures your potential difference in volts. Okay? So that's your voltage. Okay? And the question is, what is the power rating of the fan? So we're looking for power. And what would that be? V times I, which is, or I times V, it doesn't matter, 120 volts times 0.5 amps, and that gives you 60 what? Watts. Okay, 60 watts. Just like sort of a normal size light bulb. Fans don't draw all that much, okay? They do draw some, 60 watts. Okay. Now, I wish they showed the table that's on page 154. I don't think they do. I'm going to just thumb through here and see if they do. No, they do not. I'm not going to reproduce the table, but it's not a bad table to reproduce, especially in the form of an equation sheet. Hint, hint. Okay? Here's the one. I'll try to see if I get it all in there. Here's what charge is. Q is equal to number of electrons times the electron charge. Okay? So electron charge and Q in coulombs, they're just different scales. E is very microscopic. Q is macroscopic. Potential difference, work divided by time, by charge. In other words, energy per unit charge, joules per coulomb. That's a volt. Slowly sliding down. Okay. Electric current is I is Q divided by T. That's amp is coulomb per unit time, second, coulomb per second. Electrical resistance is V over I. That is ohm is equal to volt over amp. And electric power is equal to I times. Whoa. They sort of mess up. It's current in amps times voltage, but it actually comes out being joules per second. We did that calculations. I would put that whole string of identities there so you could follow it pretty easily. All right, and now we're ready to do your power bill, okay? No, electric bill, okay? And they said it right in the book. It's our energy bill. That would be the better way of saying it. What is the cost of operating a 100-watt light bulb? So what's 100 watt a measure of? That's your power, okay? For 1 hour, what's that a measure of? What's 1 hour measure? Time. That's your time measurement, okay? If the utility rate is 10 cents per kilowatt hour, so the rate is $0.10 or 10 cents per kilowatt hour. Now the book does it one way and it's perfectly fine, But to me, that's really, really convoluted. So here's what I suggested. Okay? Since this is in kilowatt hours, and by the way, 10 cents, I don't know if you're going to find anywhere that the electric charge is 10 cents per kilowatt hour anymore. Do you happen to notice on bills? My wife pays them, so I don't even notice how much the rate is. I bet you, I'm just guessing, something like 17 cents or something like that. Maybe too high, but my guess is that.
I looked it up this weekend on my farm bill and see what it is. Because our farm bill usually runs like 15,000 every 6 days.
Okay, say that again.
I'll look on our farm bill
Right.
and see what it says. Because it would be lower than normal. It's a pretty good chunk.
Okay. But you remember what the rate was?
No, I don't remember what the rate is. I'll find out.
I can remember shortly after we moved to Alabama Power was bragging on they had some of the lowest rates in the nation. And I believe they were in the single digit cents per kilowatt hour, as in 3, 4, 7, something like that. Now I'm guaranteed it's going to be more than that. Okay, so they're using 10 cents, that's fine. All right, now how the book does it is really a convoluted, hard formula to remember or use. Here's what I suggest. Since you see here this is in per kilowatt hour, just go in and change this watts to kilowatts. How many kilowatts is 100 watts? Someone say 0.1? That's absolutely right. That's how many kilowatts. You move the decimal 3 places. If you don't know that, you can do your conversion factor, okay? So there's your kilowatts, okay? Now multiply that by hours and you get kilowatt hour. Well, 1/10 of a kilowatt times 1 hour is 0.100 kilowatt hours, right? And then multiply that by 10 cents. So this is 0.100 dollars per kilowatt hour. I'm sorry, that's the rate. I've already said that. Multiply this by, got everything backwards here, 0.10, because it's the same number, kilowatt hours, which we just calculated, kilowatt hours. Kilowatt hours go out because this is the denominator, that's the numerator, and that gives you, how much did it cost? 0.1 times 0.1 is 0.01. 1 penny to run that, what was it, a fan? Yeah, no. Light bulb, 100-watt light bulb for 1 hour is 1 penny. Okay? But of course, if you have running it for more like 4 or 5 hours a night, that would be 4 or 5 cents. And if you're running, say, 8 or 10 in your house, multiply that. And that's for 1 night. Multiply that by 30, it does grow. My younger brother used to say, oh, lights don't cost much at all, don't worry about them. My dad used to say, turn off the lights if you're not using it. Okay, so different schools of thought. So anyway, that's where you get your 1 cent. The cost of operating a 100-watt light bulb for 1 hour is 1 cent. If your rate is 10 cents per kilowatt hour. Now there's also an example 6.8 there. Let's do that one in the upper part here. Electric fan draws 0.5 amps. What's that a measure of? What do we measure in amps? Oh, come on. Say again?
Flow of energy.
A flow of current. That's current. And what's the symbol for current? Capital I. Okay. So that is your symbol for current. In a 120-volt circuit, what's that a measure of? A real easy one. What's that a measure of? Voltage. Perfect. Okay? So what's the cost of operating the fan if the rate is the same as down here? Here's the same rate we used before. Okay? Now, what is the cost of operating the fan? They haven't told us how long. So what we're going to get is the cost per hour. Okay? So, how can you get anything out of that? You need to know something about the power. Does this give you power? Help me. How do you get power out of that?
You multiply current in volts.
I times V, okay? And that would be 0.5 amps times 120 volts, and that would be 60 watts, right? 60 watts. Now, because this is per kilowatt hour, I want to change that to kilowatts. How many kilowatts is that?
0.06.
0.06 kilowatt. Okay? Now, if the rate is this, if that's your power, then your cost is the power, and we don't have a time here, times the rate. Okay? And the power here is 0.06 kilowatts times your rate, which is $0.10 per kilowatt hour. Okay? So the kilowatts cancel out, not the hour part, and you get 0.006 dollars per hour, or 0.6 cents per hour. That would be the rate of using that fan. Even less than a 100-watt light bulb. This would be more like a 60-watt light bulb. So it's not costing you a lot. And that's why they say in the summertime, if you can use your fans to help keep the room cool, rather than strictly relying on your AC unit, which is using lots of power, you can actually cut your power bill pretty significantly. So keep the fans running. We didn't talk about that in the last chapter, but the heat and temperature, but how does a fan keep you cool? Does anyone know that? We didn't talk about it last chapter, but I think it's an important thing to realize. Anyone have an idea?
It seems like it picks you up, heat rises and it's just pushing the heat back down.
Say that one more time.
It seems like it would be backwards because heat rises. And
Yeah.
It seems like it'd just be pushing the heat back down.
Right. Well, that's why they say actually you can run them in the wintertime too and blow the air up there. And if you've ever worked on a ceiling, in a high ceiling in a house, it's hot up there, okay? Even in the wintertime. So if you can blow that down, that's another energy saver. But what happens with a fan, now I'm thinking more of a box fan or stand fan. The ceiling fans do okay too, but they do tend to do what you just described. But here's what's happening. Your body, as just about any body does, any black body, anything that has heat in it, it creates a boundary layer around it. So the temperature of your body is 98.6. Just a short distance from your body, it's probably down to 90 or 80. And then it drops on down until room temperature here. So you form this sort of a boundary layer around yourself. And then if you blow a fan, you blow that warm air away and let the cooler air touch your skin. So that's one way it does. But even more than that, if you're warm, what are you likely to be doing? And you are doing it, whether you realize it or not, you're perspiring. That is how your body keeps you cool. So your body is letting little amounts of water come out. And if it's right in that boundary layer, it stays pretty warm. But if you blow the boundary layer away, you're also blowing that moisture away. And remember how much energy it took to evaporate 1 gram of water? 540 calories. That's a lot. Okay? So if you're blowing that perspiration away and you're evaporating it, that's cooling you off big time. Okay? Really big time. So that goes back to the last chapter. So fans are a much cheaper way of keeping cool and maybe even warming a little bit. The trouble with a fan in the wintertime, it blows the boundary area away. So now that, remember when we talked about good insulators and the cottons and the wools and the fancy stuff that they put in coats these days, they trap dead air. That's keeping the boundary layer against you. Okay? That's what's working there. All right. Too much on that, right? All right. Before we get to magnetism, the person behind the science in the electricity part, I don't know if you ever thought of him as a physicist. You should have. Benjamin Franklin. Of course, we always think of him as a statesman, as a postmaster. But he was also a scientist and inventor. Anyone ever hear of the Franklin stove? The potbelly stove they used to have in the Cracker Barrel grocery stores, you know, and stuff. That produced far more efficient heat than a fireplace did. Fireplace, most of the heat goes right up the chimney. Yeah.
We're 11 cents per kilowatt hour.
11 cents?
That's after the taxes and everything.
Is
It's 9.84.
really? So you were down around the 10-cent range. Good deal. And what were you on? TVA?
I'm on Marshall Cab.
And what?
Marshall Cab, that's a branch off of. We get some TVA power, but not a whole lot. They're their own sector.
Oh, I see. Pretty good rate there. Hang on to it. But Benjamin Franklin was an inventor. He also was a pretty good physicist. And I'll let you read this. This cannot be your source for your paper, but this can give you ideas for your paper. They mentioned here he was one of the writers of the Declaration of Independence, played a leading role in that, so he was quite a statesman. He helped his father in the tallow and soap business, so he was a businessman, apprenticed to his brother who was a printer. He, on the side, when his brother didn't know it, started publishing. Don't know if it says the Pennsylvania Gazette, Poor Richard's Almanac. His brother got very angry when he found out he was making money on his printing thing and not telling him about it. But anyway, he was quite a businessman, entrepreneur, just all sorts of things. So he did the famous experiment with the lightning and the kite, flying a kite during a lightning storm. Fortunately, had enough sense to have a key to ground it, and so he didn't get burned himself. Just amazing what that one mind was able to do. All right, so let's move on to magnetism. All right, don't let me go too late. Oh my goodness, we're almost there, aren't we? Yeah. All right, magnetism. The earliest idea is associated with naturally occurring magnetic materials. Now, the common name for this was lodestone. Now, where that name came from, stone I understand because it was a rock, okay? Where the lode came from, I don't know. But nowadays, we call that mineral magnetite. Now, here's the unusual thing. The mineral magnetite and the mineral hematite are basically chemically identical. There is no difference between magnetite and hematite. Hematite is one type of iron ore, magnetite is another. Identically the same. The only difference is magnetite is naturally occurring magnetic, hematite is not. And it all depends on how it's settled out. We'll get to that later. Magnetism is characterized by poles. Now remember, electricity was characterized by charge. In electricity, you had how many types of charges?
2.
What were they?
Positive.
Positive and negative. Well, magnetism is also characterized, but not by charge, but by poles. Now, really the best way to name them are north-seeking poles and south-seeking poles. But we never say that. We just say North Pole and South Pole. Okay? Leads to a little bit of confusion, but we don't really delve into it that much. There are only 3 naturally occurring magnetic materials: iron, cobalt, and nickel. Now, if you happen to go to your periodic table, and it's not just happenstance, down there, kind of in the middle of all those metals, in the first row of those metals, you see iron, cobalt, and nickel. The only 3 naturally occurring magnetic materials known to exist. Okay? Now, we do a lot of things with them, make alloys and other things with them, but they've got to have that in them if they're going to be magnetic. The group name, they call these the ferromagnetic. Ferro because iron is ferrous, okay? Fe, ferrous. Ferromagnetic materials. Iron, nickel, and cobalt. Iron, cobalt, and nickel. Now, the modern view, this is all they knew in the past. And how they used it? Sailing ships, mostly. But also on land, too. They knew that, get a compass. It was going to generally point toward the north. So you could keep track pretty much of where you were. Okay, the modern view is associated with magnetic fields. Just like it's not really electricity or electrons that are doing anything, it's the electric field that's doing it. Same thing here. It's the magnetic field. Now, remember the electric field convention? The electric field lines emanate from positive charges and point toward negative charges. So they leave and go away from positive charges and point toward negative. Here, the magnetic field lines leave the North Pole and go toward the South Pole. That's just the convention they use. Point away from North Poles toward South Poles. Okay? Now, here's the difference. Electric charges, you can isolate a bunch of positive charges over here with no problem at all. Just have a pile of positive charges. You can isolate a bunch of negative charges over here, completely separate, no problem. Can you isolate a magnetic pole? Oh, wait a minute. If I had a bar magnet here, here's the North Pole, here's the South Pole. Sure, I could break it in two. Now isolated this. Because, if I pour my iron filings on it, I don't know if you know what I'm talking about there. Iron filings gather around the poles of the magnet. Not hardly anything will get around the middle. They all focus on the poles. Well, let's just break it in two. Now I'll isolate this one. No, as soon as you do that, iron filings go to this end of that is going to be south, and this end of that one's going to be north. So what you do, break them as small as you can, you're always going to have the north and south pole. So that's why they say magnetic fields, I'm sorry, I got ahead of myself. Magnetic fields and poles are inseparable. You can't have a magnetic pole without it producing a magnetic field. You can't have a magnetic field unless there's a pole somewhere in the area, okay? Now, this is what I was just talking about. Poles always come in north-south pairs. Charges don't. You can have positive charges alone and negative charges. Poles you can't. If you get a north pole, you're going to have a south pole. Okay? And as we said, field lines go from north pole to south pole, point away from north toward the south. Unlike magnetic poles, like magnetic poles repel each other, just like charges repel. Unlike poles attract each other, just like unlike charges attract each other. So there are some similarities, but also some differences. Okay? And this is what I was describing. If you had a bar magnet here, and if you sprinkled iron filings on, all the iron filings are going to go to these two ends. Almost none will be anywhere in the middle. They won't stick to it. They're all congregated in poles.
Like that?
Yes, exactly like that. In your book, if you got that, what page is that on?
132.
132. you can see now, this isn't quite completely accurate because they wiped off the ones on the end of S so you can see which is north and which is south, but that's all. They just congregate there, nothing is sticking in the middle, okay? So it shows that the field lines, and you see they're standing up like hairs, like a porcupine, okay? And that's because they're following the field lines. Now what you can't see, the field lines are going away from the north and coming into the south. You can't tell any difference in iron filings. You can't see which way the field lines are, but you know by convention what they're doing, okay? But if you tried to break that in two to isolate the north and isolate the south, immediately you make a new north, south here and a new north there. If you sprinkle iron filings on them there, here, and here. Right in the middle where there weren't any, there's where they're on. Break them again, you've made another south, another north, another north, another south. Yeah, I mean, you just keep doing. And that's why those refrigerator magnets, there's a little bitty disc. One's north, one's south. Okay? If you ever get some of those that fall off or something like that, try it. Sometimes you bring them together, you can hardly get them apart. If you flip them around and try to push them together, you can't make them touch most of the time. They're going to, the field lines will not let you do it. Okay. Pretty amazing. Okay. And this is the picture of the field lines, always emanating from the north, pointing to the south. Now, if you had a magnetic compass, okay, and you held it here, it's going to point in that direction. Here, it points there. Here, it's pointing there. Always aligns itself with the field lines in the direction, the north pointing in the direction of the field line. So, it's not pointing north anymore, it's pointing away from this toward that. It's following the field lines. Field lines are what's important. We'll talk about these later too. Okay. Okay, don't let me go too much. Is it time?
It's 5:14.
5:14. So I think we're going to have to stop there and talk about the sources of magnetic field. Let me see if I can find that. In your book. Oh, there we go. Now, some of the things in the book are not quite aligned with the slides. I think we're going to hit them all. So we'll start on page 158. That's what it is in my book, Source of Magnetic Fields. And that's where we'll begin next time. All right. Works out nicely. You have read the front page. And if you'll note, I've set up your resistor as according to the diagram on page 194. Now, the one thing that's a little different here is the voltmeter is not an external voltmeter, it's within the power supply. That's what you read on your scale. So, that's why you don't see a voltmeter. But the one you see over here is an amp meter. It's a multimeter, but we're going to set it for ammeter. Okay? So, you set it up, we set it up like this. You will adjust the DC adjustable power supply as instructed by me. And here's what I want you to shoot for. Now, your tables you're going to be filling out. You got two identical tables. The first one, table 22.1. They're not quite identical, but close. Okay? 22.1. Got it? Now, the voltages I say to aim for are just like the trials. 1, 2, 3, 4, 5, and 6 volts is what you're going to aim for. Now, your current, we're going to have to fiddle with the ammeter in order to read it. Okay? So I'll try to come set it up the first time, and then you'll need to deal with that. Now, I'll tell you right now, the ammeter is not going to read amperes. It's going to read milliamps. So how are you going to convert that to amps? 3 places which way? To the left. Okay? Yeah, okay. Because if you read something on there, let's say a 23, that'll be a 0.023. Move it 3 places in front. Because 23 milliamps is way less than an amp. So it's 0.023. I just made up that number. Yours will be very different from that. Okay? So I'm going to help you set up the first time. And I'm pretty sure they're all scale almost immediately. Tell me before I get beyond the amp. I'm going to get 1 volt. Oops. Not there yet, right? So I'll turn this off. Try it very slowly to get up to 1. Oops. Can't do that anymore. Okay? Now, very slowly get up to 1 volt.
When the local chicken,
You're going to have to play. This is a drifter, I think. So when you get it sort of stable, read the current. Now this is an milliamp, so you're going to have to move the decimal 3 places. Okay? I think we're going to be starting on that scale. Yeah, yours was a little more stable. No, it isn't. This is drifting too. Okay. Now you may not be able to hit 1 volt on the nose, but that's going to be fairly close. You can play with it and see if you get 1 volt. Shoot for 1 volt. Oh man, he's pretty fiery, isn't he? Okay. This is a milliamps to record your data. If it's not 1, do 1. Yeah, perfect. Any questions asked? Don't assume.
So the black thing is our amps.
How many? That's milliamps.
And we, okay.
Yeah. Move it 3 places, decimal 3 places to the left. Say again? This is volts, yeah. I mean, right here.
We're focusing on the black
Yeah,
hole.
down to 1. Okay. I know, it's real jump. Okay, if that's as close as you can get, go with it.
Oh,
That.
8.37. 8.5. 8.53. 8.5.
No, it probably won't.
8.7.
3 places we got. 0, 0, 8. 3, 7, 4. I don't know why it's shifting upward like that, but it is. Then go to 2, 3, 4, 5, and 6. If you have any questions, please ask. Be gentle with my equipment, please.
Can we bump it up to 200?
That's what it was.
Yeah, I think so.
Oh, my thing is maxed out.
What's that?
Do we bump our multimeter up to 200 milliamps when we,
Yeah. If you, okay, if at some point, and it will happen, you go off scale, then move it. Okay. Okay. Yeah.
Yeah, ours says 2.
Sorry.
Ours just says 1, 2. What do we?
What's that? Okay, yeah.
I think it's some point.
7.8, which is 0.0278.
I didn't speak
If you have any questions, please ask.
only one have been 0.007. Wait, what did, okay, then it's high.
No, we're not.
We're at 20.7 right there.
We're 2 points. Wait, your honors college line.
We're on there, it's fluctuating to 88.3.
Other questions? Yes.
What are we putting with resistor?
Oh, I'll give you that in a minute.
Okay.
Okay. Have you finished?
Yes, sir.
Okay. We're gonna turn that off. Off. Okay. Now, let everybody else catch up. Just a mild announcement. I've received the 4th research paper, which means I only have about 9 more to go. So please get those in sooner rather than later. If there are no questions, I'm going to pause the... All right. If you're following on your lab sheet, what you've done is on page 194, Part A, and you've done 1 through 3. Okay? Right? Now, skip Part B for now. We're coming back to it. And look at results number 1. Make a graph of the 6 data points from data table 22.1. That's the one you are filling out by placing the current on the horizontal axis, the x-axis, and the voltage on the vertical axis. Now, I need to get approximately your ranges. I think most everybody is 1 to 6 on the volts, right? Okay. What are your amps approximately? And that's 0.00.
0.00887 to 0.05.
What's that?
I'm sorry.
I'm so sorry.
Come on. You're just like,
It looks like
you don't have been any quicker. You
you
can
got
take it.
there.
Or zero's okay.
8 to 50 there.
Mine calculated.
You were the one reading it off to us. If we're wrong, it's
Okay, so I would say that's the current. I would say if this is indicative, then put your, they said the current on the horizontal axis, to do it in landscape mode like this and go across like this. Now, you had about 1, 2, 3, 4, 5, 6. Ten, I think it worked. 0, yeah, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07. And then you go 1, 2, 3, 4, 5, 6. Okay, so I'd say put it in landscape if that'll work for you. Now, I didn't see your numbers. What were your ranges?
I mean,
8, yeah, that's about the same.
I mean,
I think you do it like this will work. And what were your ranges? Oh yeah, well done. Very, very close. Okay, so if you heard what I was saying, your voltage are easy. 1, 2, 3, 4, 5, and 6. Okay? Your currents will be something like 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, and that'll give everybody. Zero, 1, 0, 2, okay? And plot your graphs. Meanwhile, and still your
I'm not ready. I'll be in commentary. These are the normal ones. I think it's because of the 1, 2, 3, 4. I'm just saying. Yeah, they were. It's just because they were so good.
okay. Once you've plotted your points, then get your ruler and draw the very best straight line as close as possible to all 6 points. If it helps, you can use 0, 0 as a 7th point. If it hurts, don't do it. Okay. Okay, everybody has graphed their points, drawn the best straight line, And now calculated the slope. Number of voltage divided by number of amps, which gives what unit? Ohms, okay? Now, it says says calculate the slope, which you just did. Write it here and somewhere on the graph. Did you do that? Okay. Number 2, compare the calculated value of the known resistor. I'm going to tell you what it is. You've got the calculated with the accepted value. The accepted value is, drum roll please, 100 ohms. Okay? Now, it says calculate the percentage error. Now, let me show you, in case you've forgotten, how to do percentage error. That's not any good. Okay, your percentage error is your measured, that's what you calculated, minus the actual, okay? Some of you, your measured was a little bit more than 100, some of it was a little bit less. Those with more, it's going to be a positive error. With less, it's going to be a negative error, okay? And divide it by the actual, okay? And that will give you a decimal number. Move the decimal 2 places to the left, and you get the, yeah.
So it's
Okay. Since your denominator is 100, basically, yeah, well, your, let me see what you do and then I'll tell you the shortcut, but I want you to do it first. Absolutely. How did y'all do? Okay, so that would be 2%. How did y'all do? All right, good deal. So you write that also on page whatever I was just on. All right, that was on page 194. Calculate the percentage error. Put it there. Now, while y'all were sleeping, while y'all were doing your other stuff, okay, I put new resistors in. So you start back over, just like you did before, and repeat procedure A. We're back to page 194. Repeat procedure A with an unknown resistor. That's what's in there now. On this one, you'll put the data in data table 22.2, which is on page 198. 1 through 6 on volts. Your currents, I think, will be less. So you'll probably stay on that first, 20, a little bit long. I don't know if you'll stay there permanently. See what you get.
let's start with 1 volt.
Might get a little more precision. It's not a lot.
Yeah.
Try it a little bit smaller. Oh, it's past time. Let me call roll again. I'm going to turn off my recording. I don't need to record the roll. We did everything on page 194. Those 2 questions dealt with the first graph, the known resistor. Okay? Number 3, make a second graph which you did, 22.2, placing current on the horizontal, voltage on the vertical. Did you calculate the slope and write it on number 3? Everybody? Okay. And just call out some of those slopes.
407.
Okay.
394.
Okay. Now,
384.
okay. Now, what is the value of the unknown resistor? 390. 390 ohms. Okay? That's all you have to put for number 4. Number 5. Explain how the graphs demonstrate Ohm's law. Say again?
Rise up.
The more voltage you have, the more amperage you have.
Okay? And what is Ohm's law? Give me a representation of it, especially in terms of resistance.
It's voltage equals the current times the resistance.
Okay? Solve that for resistance.
So resistance equals voltage divided by current.
What were you doing when you measured the slope of the graph? Rise over rise.
Divided
Voltage by resistance. That's Ohm's law, isn't it? That slope gave you the resistance. And you answer number 6 however you want to, positive, negative, or whatever. A blank gets you no credit. Any answer gets you credit for that. Any questions? Everybody hunky-dory with it? Well, I'm going to end recording unless there's questions.